Hello, my name is Valentin and today I represent our work DIMMER, a self-adaptive network-wide flooding protocol that uses reinforcement learning. Network-wide flooding is a very interesting and very efficient paradigm in low-power wireless networks. What it does is simply it transforms a multi-hop network into some kind of logical bus where every device is able to communicate, transmit and receive from every other device regardless of a distance. There are multiple protocols that build on this idea in the literature, and some of them show that network-wide flooding is able to survive harsh interference if it is well tuned. So we ask ourselves the question, how can we build an adaptive network-wide flooding protocol? A protocol that is able to tune its parameter to survive harsh interference, if there is any, but also to save energy if the conditions are good. And there are a few challenges with that. Many of the protocols in the literature don't have some kind of feedback. Some of them don't even have acknowledgements. So they don't know whether the flood is going well or not. And also, when you have a wireless bus, you kind of lose your notion of neighbors. You don't know who are your direct neighbors anymore because you are able to communicate directly with every device. And of course, when we look at tunable parameters, in our case, it's going to be the number of retransmission, the number of times we transmit the same message within a flood. The optimal values of this parameter are depending on both your topology and also the interference you're going to face. And some of these are unknown in advance. So it's difficult to know which value is going to be optimal for which interference. That's where our contribution comes. We present DIMMER, which is an all-to-all network-wide flooding protocol. The interesting part is that DIMMER is self-adaptive. It learns by itself how to detect and react to interference. To do that, we use reinforcement learning and we train it on unlabeled data. We don't know what are the optimal values. The reinforcement learning agent will try out different values and learn by itself which are optimal. And we also use multi-amp bandit to be able to optimize energy efficiency at runtime and react to interference. DIMMER is embedded, that means it runs its neural network on some small constrained devices with only a few kilobytes of RAM. And our implementation is open source, that means you can just check it out and run it yourself if you wish. How does DIMMER work? So basically, DIMMER works in communication rounds. For example, every 10 seconds, devices will communicate, will send some packets using floods, and 10 seconds later, they will do that again. In DIMMER, we add some feedback to the packet propagation. More importantly, we send the reliability. How many packets did we receive lately? How many packets did we lose? And also, how much energy did we consume using the radio to communicate? All of this feedback is collected at a central device that runs its DeepQ network. That's its reinforcement learning neural network. And this DeepQ network will tell us if there's interference or not, and which parameter should we use. Again, our parameter here is the number of times we retransmit the same message within a flood. So here is a small example. DIMMER is communicating in rounds, and there is some interference. DIMMER, with its feedback, will detect it and will decide to increase its parameter so that we have more chances to survive interference. And when the interference stops, DIMMER will also detect that and will decide to change once again its parameter, this time to save energy. So how can we train this DeepQ network? Basically, we have a deployment in our offices and we run many experiments testing different parameters. And at the same time, we inject interference. That means we use Wi-Fi on the side, or we use other devices that will just transmit at full power to try to break communication, to create interference. We run many of these experiments, and we collect all of them, and from these data points, we create some kind of simulator. Basically, what the simulator does, it's able to replay an interference, how it turned out in the real world. And then the reinforcement learning agent is able to try out different parameters during the interference to see which one works best and how to develop a strategy to counteract interference in general. So we train this neural network And once it's trained, we can take it and embed it into these small constraint devices. So basically what we do is we quantize the neural network so that it fits in memory. And that's it, we have dimmer and we're able to run it on the devices. So let's look at the small evaluation. Here we run two experiments. The first one is the baseline. We don't change the parameters. And the second one runs dimmer. So it uses its self-learned neural network to adapt to interference. On the side, we jam the wireless medium. That means we create interference. We use other devices that transmit at full power to try to break communication. And here you see that reliability drops whenever there is interference. So as soon as there is interference, we lose packets. And the stronger the interference, the more packets we lose. But with dimmer, dimmer is able to detect that there is interference, and it will change its parameter to counteract it. And with dimmer, you see that we lose fewer packets because we detect the interference and we adapt to it. And also, once the interference has stopped, dimmer is also able to detect that and go back to some normal optimal parameters when the conditions are good. And again, remember that we train on unlabeled data, so we don't know which parameters are optimal. Dimmer learned by itself through the simulator which parameters it needed to use to counteract different levels of interference and when the conditions are good. Then we ask the question, we did this experiment on the same deployment as the one we used for the training. What happens if we take our neural network, but run it in a different deployment with perhaps more devices and with unknown interference we have never seen before and we have never trained for? So we tried that as well in our evaluation, and we show that dimmer is still able to maintain high performance. That means it's still able to detect and react to interference, even if it doesn't know this specific shape of interference. And it's also able to optimize energy. That means it's able to detect when there is no interference and which parameters are the best to save energy in that case. So I just gave you a glimpse of dimmer, which is a self-adaptive network-wide flooding protocol. Dimmer is interesting because it learned by itself using reinforcement learning, unlabeled data, and embedded neural networks how to detect and react to interference and how to save energy. We show in our evaluation that dimmer works on new deployments against interference it has never seen before. All of that without the need to retrain the neural network. Thank you for your attention.